So for this week, as we talk about the center of the Earth, we need to review from 6th grade the 3 types of heat transfer: conduction, convection, and radiation. This image is from your worksheet. We are going to come back to this in just a minute. First, we are going to define the 3 types of heat transfer. So first of all, oh, that's annoying. Radiation is first. Okay, so radiation. Who can tell me what is radiation? Types of heat transfer, yes.
Well, they use it in microwaves.
Okay, it's used in microwaves. How about a definition for that?
Like, it keeps this all around,
Kind of. So all around, the key with radiation is that it can travel through empty space. It can travel through empty space. It does not have to be touching anything. It does not have to have solid, liquid, or gas. And radiation, of course, from the sun, the sun thankfully is not touching the Earth. And you also know that there's empty space between the sun and us. The sun is 93 million miles away, but is the primary source of all heat, of most of the heat on Earth. So radiation, heat traveling through empty space. And as we showed with our other example, radiation can also be given off as light. If you have an electric stove or an electric heater and it glows red, that's radiation, that's heat being given off as radiation. So light, glowing, and things like nuclear radiation, radioactive things, that's another type of radiation, higher energy. It's a little different than the heat transfer, but the key for radiation, it's traveling through empty space, and it does not have to be heat rising. So the next type of heat transfer we have here is convection. Now, we just talked about convection a moment ago. Convection is heat transfer how? You all forgot? You just wrote it down. Convection happens in gases and liquids, only in gases and liquids. Convection cannot happen in solids. And I remember by thinking of convection currents, currents of warmer, less dense air or water rising, and the cooler or more dense sink. This is responsible for the heating of the atmosphere. We're going to tell you in a minute kind of how this applies to the Earth. But if you think of a pot of water boiling, it gets warmer first at the bottom, right? But then the warm water rises, becomes less dense and rises. And so you get, I mean, it's actually called a rolling boil. When it gets to boiling really hard, the warm water circulates. So convection currents in gases and liquids. Okay, and then the third type of heat transfer is conduction. And conduction is heat transfer, and the two surfaces or the two substances must be touching. So conduction can only happen when two things touch. So in this case, if you have a burner heating your pot of water, the pan is touching the burner, the water is touching the pan, and that's how it heats. So the two things must be touching. So that makes it easy generally to figure out which type it is. Conduction, it has to be touching. Convection, gases and liquids. Radiation, through empty space. We will come back to these this year several times, so good for you to practice these and know these. And the textbook gives an example, I think actually I have another slide of it, of the pan of boiling water, because you can see all 3 types of heat transfer there. So if we go back to this, right, picture number 1 is what? Conduction, convection, or radiation? What is this? Convection. How do you know?
Because the arrows are moving in a circle.
Okay, excellent. So we had 2 things people said, because there's liquid. Okay, they're showing arrows of the convection currents. What's happening here? Is that convection too? Yeah, we've got convection happening in the air here. So you got 2 types of convection. Okay, now the middle picture, which is kind of annoying because you're like, oh, it's a swimming pool with a beach ball in it. What type of heat transfer is happening here? I'll give you a hint. It doesn't have anything to do with the beach ball. Yes. Yes, and why do you say radiation? Good. So the sun will heat up the swimming pool and the beach ball and the ladder and all those things. Traveling through empty space, heating it up. Okay. And, oh, sorry, so that was radiation. And this last one, kind of confusingly, we have another boiling thing. Conduction, why?
Because the hot is touching the stove.
Okay, good. So you've got the hot burner on the apparently electric stove touching the tea kettle. The tea kettle touches the water, and so it heats up that way. Okay? So that's that. Again, you will see these over and over again. This will definitely be on Friday's quiz. So let's jump now over to the worksheet you did earlier. Yesterday you did this worksheet. We're going to do some notes from the chapter, but you can follow along. You might have this out with you, and then we're going to take some notes from what you read. So we're going to talk about the inside of the Earth. When you look inside the Earth, let's go ahead and clear this. Took your notes already? Okay, perfect. So let's add to that. When we look inside the Earth, we have the three main layers of the Earth, right? We have the crust, which is the outermost layer. And we have the mantle, which is the thickest layer. And then we have the core. Okay? And the mantle. We said that already. So the crust, is the outermost, and it's the thinnest layer. And the textbook gives these to you in kilometers, which is good because scientists use kilometers, but I think it's a little confusing because most of us don't think in kilometers. If 1 kilometer is about 0.6 miles, if you want kind of a ballpark figure of how many miles it is, a kilometer, 0.6 is close to what easy number? 0.5. So, I mean, it's 2/3, but easy ballpark figure, you could think half, right? So the crust, 5 to 70 kilometers thick. How many miles thick is the crust? 5 kilometers. So what's half of 5? 2.5. So 2 miles thick up to 35 miles thick. That's how thick the crust is. Okay? So at its thinnest part, the crust is thinnest under the ocean. Yep. Thinner, denser crust. And again, at the thinnest part, we're talking about 2 miles, right? And then the thickest part, as somebody just mentioned, the continental crust, and that would be on the continents, of course, and on the mountains. In the mountains is going to be thicker parts, and here you're going to have less dense. It's made of slightly different types of rocks, and it can be, according to this, up to approximately 35 miles thick. Okay, so then next we have the mantle. The mantle is the thickest layer of the Earth. When you look at the cross section of the Earth, most of that is mantle. Now, the mantle is divided into 2 different layers, and this is a little bit confusing because the lithosphere, lithos means rock, and this is the upper layer of the mantle, but it's actually kind of confusing because the lithosphere is actually technically the crust plus the upper mantle equals the lithosphere. Now, why would we have a separate layer for that? Because that's what the tectonic plates are made of. We've talked about the plates are moving. which we'll get into a little bit more tomorrow as we read the next section. So the plates on the surface of the Earth, the crustal plates, are actually made of the crust in the very upper part of the mantle. That's the lithosphere. And then here is probably the most confusing but the most interesting layer, the asthenosphere. So the asthenosphere is very interesting because it's kind of solid, but it has convection currents, which means it can't really be solid. It has, it's relatively hot, and it has what's really best described as kind of a silly putty texture. You guys know silly putty, right? Seems like it's a solid, but if you make your silly putty into a nice round ball and set it on the countertop and leave it overnight, what happens to it? It kind of melts, it kind of flattens. So it's kind of a solid, but it's not truly a solid because it doesn't hold its shape. So the asthenosphere has this odd silly putty texture, and because of this, it can have convection currents. Now this is very important because this is what's going to be responsible for the plates moving, which is what's going to be responsible for earthquakes and volcanoes. So convection currents in the mantle. Now, in that model we just saw, the water was the mantle. What's heating up these convection currents? From the core. I'll get your question in just a second. So the core is liquid. The core is actually, it's very dense. It's liquid, mostly iron. It's metal, magnetic, very hot. And the mantle touching, the core touching the mantle is what's going to heat it. And in the very center of the inner core, scientists believe there is a solid inner core that's actually hotter and denser, and the only reason it's solid is because there's so much pressure that the molecules can't move. It is really cool. It's actually really hot because of extreme pressure. Now, the interesting thing about this is the deepest mines or holes we have ever drilled go how deep? Just in the crust. We have never actually dug deeper than the crust. So how do we know this about the center of the Earth? Let me get a couple quick questions, and then we'll move on. So what we're going to get to in the next couple days are actually some of the plate boundaries. And yes, the boundaries between plates, earthquakes are the plates moving side by side, and in some cases volcanoes are the plates moving apart. It is not the mantle or the core coming up, just melted rock. But let's take a look, at this. So how do we know, if we have never drilled past the crust, how do we know that what's inside the Earth? You may have read about this. If you take a look, the textbook started talking about direct and indirect evidence. Direct evidence is something you can actually see or measure directly. Now, indirect, you have to kind of figure out without looking, right? Like shaking a box and trying to figure out what's inside the box just by the weight, how it feels, what it sounds like. We have some very interesting indirect evidence about what's in the center of the Earth. So this, I think, is a very strange picture and kind of a confusing picture. This is a picture of an earthquake, and this says it is the path of seismic waves. Now, remember we talked about P waves, which are the fastest waves, which are compression waves, right? And then we had the S waves, which are the side-to-side waves. When an earthquake occurs any place on the Earth, it travels just like if you dropped a pebble in the pond and those waves go all the way out, a similar thing happens. And when the waves hit different densities of water or something solid in the way, they bounce and they change speeds. And so because of this, we know that inside of the Earth are different densities and different temperatures by where the waves can be felt. Okay? Now, how do we know there's liquid in the core? Okay, and so the reason we know that there is a liquid core is because not all waves can travel through liquid. And your magical homework is to figure out if it's the P waves or the S waves.
It's the P wave.
Now don't guess. Oh, guess what?
It's
The S waves. So scientists can tell seismic waves tell us about the Earth center. S waves, that's S waves. My smartboard read that as a 5. S waves cannot travel through liquids. And so because of that, we know that part of the core is liquid and that part of it is solid. We just did that. So, and then this is the demonstration we did in class today to remind you. And what we're going to read about tomorrow is how this is causing the continents to move. And the fact, and this is actually a relatively new idea that the continents are moving and that they are moving because of this. And in fact, when Alfred Wegener first proposed this theory that the continents were moving, people didn't believe him because he couldn't explain what could possibly move the continents. Yes. So this is conduction, convection, radiation. And later this week, on Thursday, we will do another flip lesson on continental drift.